Okay, I think we'd probably better make a start then. So welcome everybody to this advanced OpenMP course as part of the ARCHER2 training program. Just going to start with a few bits of administration before we kick off with the first lecture. So the legal stuff to begin with, so you are free to reuse this material. So all this is under a Creative Commons license. So all the material associated with this course is free to reuse, provided you provide the appropriate credit to us. Okay, and so yeah, this is provided as part of the ARCHER2 service, which is administered by the UKRI, so basically the government research body in the UK. Ourselves, EPCC, which is part of the University of Edinburgh, and also by Cray, who provide the hardware for the ARCHER2 service. So in case those of you you're probably quite well aware of what ARCHER2 is. It's the UK's national supercomputing service. It's housed, operated and supported at EPCC and the University of Edinburgh, and Cray supply the hardware. And this training is provided by the CSE support team. So I think we do, I think we do more than 60 days per year now. And it's available to all academics. Okay, a little bit about ARCHER2. So the full system has just under 6,000 nodes in it. It's 128 cores per node. So each node has 2 AMD Rome EPYC chips with 64 cores each. So that gives us just under 750,000 cores in total. There's 256 gigabytes per node of memory, except for a few large memory nodes which have double that. It uses Cray Slingshot interconnect and has basically file systems. There's actually 4 separate Lustre file systems and a burst buffer file system to support it. Okay, useful links, which you're probably all again already aware of. So all our this and upcoming courses are at the training link. The material from past courses is all archived, and so the material in particular, the material from this course will remain on the ARCHER2 website sort of semi-indefinitely. So you can always refer back to that, and that will include video recordings of the sessions. There's also various virtual tutorials online, and there's also the documentation for the system itself, which you might find useful if you're running the practical sessions. Okay. Introduce myself a little bit. My name is Mark Bull. I'm a senior research fellow at EPCC. I also teach on our master's program in high performance computing, and I'm the representative for EPCC on the OpenMP Architecture Review Board. So that's the body that administers the OpenMP specification. Other things, tomorrow I will point you at a feedback form for this course and give you a little bit of time to fill it in. So that's always very helpful for us to figure out what you like about these courses, what we'd like us to do differently, and what other things you might like to learn about. If you have problems with your account that that we can't solve immediately, then please contact the help desk. Okay, yes, we run a master's program. Okay. Access to ARCHER2. So you have had the opportunity to sign up for a project account. So this comes with a small amount of CPU budget. We're actually not going to use reservations for this course. We should. There are few enough attendees that things should go through very quickly anyway. If you already have an ARCHER2 account of your own, then you're absolutely welcome to use that as well. In either case, can use the short queue to get quicker job turnaround for the practical sessions. The accounts will be closed approximately 2 weeks after the end of the course, and everything in it, all the files in those accounts will be deleted. So just remember, if you want to take any copies of things that you've written or anything else that's in the training account, please copy them off before then. Okay. And yeah, okay, as already mentioned, the course materials are on the ARCHER2 website, and they will be archived there for future reference. Okay. We operate these courses under a code of conduct, which basically says that everybody should behave nicely. Both for ourselves and for anybody attending the course, we ask you to use welcoming and inclusive language, be respectful of other people, accept constructive criticism. So that's largely for us, I guess, and focus on what's best for the community, and just generally being kind and respectful. Okay, so in terms of what we're going to cover, so today we're going to start off with some lectures from me on, we're going to cover OpenMP tasks, nested parallelism, and the memory model. And then we'll have a break, and then there'll be an opportunity for you to do some practical exercises. So I'll be around online during the practical exercises if you need any help or if you have any questions about them. And then after lunch, we'll have lectures on sort of general hints and tips, tricks, and pitfalls for practical use of OpenMP, and then we'll talk in more detail about performance issues and tuning. And then the final session will be is another practical session. You can have a go at. I'll give you a not very well optimized piece of OpenMP code, and see if you can find out what's wrong with it and improve the performance. And then tomorrow we'll move on to hybrids programming with OpenMP and MPI in the morning, and then in the afternoon we'll look at some of the more recent features that have been added to OpenMP. Won't be an exhaustive coverage, but some of the more interesting and useful ones. And we'll also look at the target offload capabilities in OpenMP. So ARCHER2 is essentially a CPU-based system. We have very recently taken delivery of a small test small number of GPU nodes with AMD GPUs in it. Unfortunately, we're fractionally too early. They've been in, the hardware is there, but they're not available to users quite yet. So we won't be able to have hands-on experience with them this week, but at least you'll have had an introduction to how to program GPUs with using OpenMP. And if you are an ARCHER2 user, then you will there will be mechanisms for getting access to the GPU test cluster coming up shortly. And then we'll have a session after the break, and if anybody, if there's any more help or assistance needed, or I'm also very willing to answer questions about codes that you are working on, or particular things, anything else that you might be interested in. So that's opportunity for you at the during the last session, is to basically ask me anything you like within reason about OpenMP, say including if you want to ask about the things that you're working on, then I'm very happy to help. Okay, yeah. So all the materials, just go to the ARCHER2 website and follow the links to this course under the training tab, and then there's a button that says course materials, and that will take you to a Git repository which contains all the materials for this course. Okay, so the source code for the exercises is in the Git repository, but there's also a copy already in a shared directory on ARCHER2, so that you can, if you log on to ARCHER2, you can just take a copy of the tar file that contains the source code for the exercises and unpack it. So just note that you can only submit batch jobs from your work directory on ARCHER2, which is not the default place that you end up in when you log on to ARCHER2. So just be aware of that. I recommend that you do everything in your work directory, and then that allows you to submit batch jobs from there. It's absolutely fine for if you're developing OpenMP code during this course. It's fine to just compile and run stuff on the login nodes. The examples running are short and have short run times. They only take up to half a minute or something to run, is about the longest one. So while you're just developing code and testing it, it's absolutely fine just to run stuff on the login nodes. If you want to actually make some performance measurements, then you won't get terribly reliable timing behavior on the login nodes, because they're shared and with all the other users that are logged in. So if you want to make timing measurements, then you should submit a batch job. Okay, I hope you enjoy the course. Encourage you, please ask questions, and probably the most convenient way to do that is via the chat facility in Collaborate. So say this is slightly browser dependent, but you should see on the Collaborate page there is a purple arrow in the bottom right hand corner, which allows you to, if you click on that, it will open the Collaborate panel, and then there's like a speech bubble icon at the bottom, and that's the link to, if you click on that gives you access to the chat. So if you want to ask questions, please type in the chat window, and I'll keep an eye on that. And my colleague William, who's also logged on today, he'll also help me out by keeping an eye on the chat window and pointing out to me when there are any questions. Yeah, that's probably the easiest way for us to operate. But yeah, please feel absolutely free to ask questions at any point during the session. Okay, so anybody have any questions before we start? In which case, let's crack on with the first topic, which is OpenMP tasks. Okay, so what most people tend to do is with OpenMP is straightforward parallelization of loops with the parallel for or parallel do directives, and then also maybe use some of the synchronization constructs, so atomic updates, critical regions, barriers, maybe lock routines, and that gets you an awful long way with a lot of applications in OpenMP. For applications that are not structured in that way, so don't have, don't use the classic loops or nests of loops running over multidimensional arrays, which is a very common pattern in scientific computing. For more irregular computations and for different expressions of parallelism, then tasks is a useful feature. So let's have a look. Okay, so what are OpenMP tasks? So really, tasks are just a way of letting us as programmers identify independent units of work. So tasks are really composed of two things. So there's a block of code to execute, but there's also potentially some data to compute with, which is private to that task. Okay, so we can have copies of data items, copies of variables, which are private just to that task. Okay, so you'll already be familiar with the idea of private variables in OpenMP, but maybe what you've come across is private to threads. Okay, so that's the classic use of, or classic meaning of private variables in OpenMP, is that every thread gets its own copy of some memory location. But with tasks, we also have the opportunity that individual tasks can also have private copies of memory locations associated with them. And so what's going to happen is, as a programmer, we're going to identify the tasks, going to identify the blocks of code that can be executed in parallel, and potentially the private data per task to compute with. But then the runtime is going to somehow assign the tasks to threads for execution. And as programmers, we have very little control over how that is done. That's really down to the runtime to decide how to do that. So what it will try to do is try to load balance the tasks across the threads inside a parallel region. It'll also try to do things so the task scheduling algorithms can be quite sophisticated in OpenMP implementations. They will try to not just load balance, but also schedule tasks in a way which is efficient for cache reuse as well. So a little bit more about tasks. So task construct includes a structured block of code. So structured block here really just means a block of code where the control flow goes in at the top and out at the bottom. So it's just the same as most other OpenMP constructs, which have a structured block associated with them. You're not allowed to branch in or out of that block of code. So as with other OpenMP constructs, tasks only really make sense or will only do anything useful if we're already inside a parallel region. So in OpenMP, parallel region is the only mechanism for creating multiple threads. So the task construct itself does not create threads, and it only does something useful if we're already executing inside a parallel region. So if we're inside a parallel region, a thread that encounters a task construct will essentially package up that code block and any associated data for execution in the future. And some thread in the parallel region will execute the task at some point. So as I say, we have very little control over which thread will execute a task or what order they're going to get executed in. And in principle, actually, it could be, at some point in the future, it could be now. Okay, so it's perfectly legal for the implementation to execute the task on the encountering thread right now. Okay, so that is a possibility. So in general, that's not what happens, because that won't in general produce very good load balance. But there are cases where that can happen. And one of the powerful features of OpenMP tasks is that tasks can be nested inside each other. So a task itself, the code block inside a task, or any routines that it calls, may in turn contain other task constructs. And so a task may generate subtasks, and subtasks may generate sub-subtasks, and so on. So we can have any amount of any depth of nesting of tasks that we like. So that can be quite a powerful feature, and we'll see an example shortly of how that can be used and why it's an interesting feature. Okay, so task directives, no real big surprises. What the syntax looks like. So $OMP task and OMP end task in Fortran, and for C and C++ hash pragma OMP task. Okay, so actually this would be a good point to ask everybody who's online today. Are you primarily a Fortran programmer, a C programmer, a C++ programmer, or are you some combination of multilingual in those languages? So if you could let me know by typing in the chat box now, that would be really helpful, so I can decide which of the base languages to place more emphasis on. Okay, 1 Fortran, 2 Fortran, 3 Fortran. Okay, all 3, C and Fortran. Okay, C++, but also speaks Fortran. Very good. Okay, 1 C programmer. Okay, thank you. That's helpful. So we've got a mixture. So I will not ignore either, or no, I will try not to ignore any of the base languages. So some of the examples are in one language, some are in the other, some are in both Fortran and C. But I will try and be sort of equal-handed with or fairly base language agnostic for these sessions there. Okay, rather C-based here. Okay, but I hope you can. It's sufficiently easy for you for Fortran programmers to translate for themselves. Okay, so very simple example. Okay, so let me find a pointer. Okay, so to emphasize, so we need to be inside a parallel region for any of this to make sense. And a very common pattern is for tasks is to have only one of the threads inside the parallel region doing the task generation. Okay. So at first sight, this looks a little bit odd. If you look at this piece of code, it looks like there's this master region in there which says only thread 0 execute this. So this pattern at first sight looks a bit strange. And you'll also see sometimes, you also see parallel single done as well as a basically equivalent version of this pattern. So it really doesn't matter whether it's thread 0 or not that does the task packaging. This is a very common pattern. So inside a parallel region, and one thread only encounters all the task contracts. So here we have we've got 4 function calls, each of which has a task directive on it. So that identifies those 4 function calls as independent tasks for execution. So what's happening here is that thread 0 is packaging the tasks, but it is not, at least in the first instance, it is not executing them. Okay, these tasks will be executed by some thread inside the parallel region and in some unspecified order. So that leads us to the question is, okay, so if tasks just get executed at some point in the future, how do we know when or where in the program can we guarantee that tasks have been completed? So there are several ways of forcing task completion or waiting for previously generated tasks to complete. So first of all is at thread barriers. So that can be either explicit barriers or it can be the implicit barriers, for example, at the end of work sharing loops or the barrier at the end of the parallel region. So wherever we can encounter a barrier, then that barrier will wait. The barrier will not complete until all the tasks generated in the current parallel region up to that point have actually been executed. And we also have some other mechanisms. So the next one is the task wait directive. So this says wait until all the tasks defined in the current task have completed. Okay, and this is like as with the barrier directive, this is a standalone directive that has no code associated with it. This is what's called a shallow wait, in that it applies only to tasks generated in the current task. But if we have nested tasks, it doesn't apply to descendants. Okay, so it only applies to the immediate children tasks of the current task, but it doesn't wait for the grandchildren or great-grandchildren tasks. Okay, so the way this is worded, it kind of says, well, this only makes sense if we have nested tasks, but actually it works without nesting as well, because the code executed by a thread inside a parallel region is considered a task for these purposes. So the way it's worded in the specification is that's an implicit task. So the block of code that a thread executes inside a parallel region is actually an implicit task. So it counts it counts as what's meant by the current task in this context. So without nesting, if we call a task wait, and basically it says this will wait for all the tasks that have been generated by this thread up to this point. There's also another way of doing this, which is the task group. So this does have a structured block of code associated with it. Okay, so in Fortran it looks like task group and end task group, or in C and C++ hash pragma OMP task group and a structured block. And this, the end of the task group will wait until all the tasks that have been created within that block of code have completed. And this is a deep wait. So this actually does apply to all the descendant tasks. So again, simple example here. So again, suppose we have this. So we're going to use this parallel master pattern again. So the master thread is generating these tasks. Okay, so it generates a task that contains the call to Fred. It generates a task that contains the call to Daisy, and then it calls task wait. So at that point, the master thread is blocked and cannot proceed until the Fred and Daisy tasks have been executed. So probably by some other thread in the parallel region, but not necessarily. Okay, so the master thread could itself also participate in executing, say, one of these tasks. So that means that the task that contains Billy cannot be generated before Fred and Daisy have completed. So that's one way of coping with dependencies between tasks. So this enforces some. So you can use this to enforce some ordering. So this means that, you know, if Fred and Daisy compute something that's going to be used by Billy, then this is one way of specifying that ordering. It's not necessarily the best way. There are other ways of doing it, but in this case, that's what it would achieve. Okay, so let us look at a slightly more interesting example. So example I'm thinking about here is doing a traversal of a linked list. Okay, so a linked list is just a data structure where every item in the list contains a pointer to the next item. So, you know, it's a very classical data structure. And so suppose we have the situation where we want to do some work on every item in a list, and it's a big enough piece of work that we'd like to do those, we'd like to parallelize that. So in this case, so let's just walk through this little bit of code here. So what happens at the beginning is we get a pointer P that points to the list head. So that's the first item in the list. And then we loop. So while P is a valid pointer, so while P is not a null pointer, then we're going to call this function process. So that's the independent piece of work that we want to do on every item in the list on the current item. And then we can call this next function, which will return the from the current item, will update P to point to the next item in the list. So we keep going through the list. Eventually, the last item in the list will have a null pointer to the next item, and the while loop will terminate. Okay. So this is an example where we can't use a OpenMP loop directive. We can't use OMP parallel for, or equivalent in Fortran OMP parallel do, to parallelize that, because the restriction on using those directives is essentially one that ensures that the number of iterations in the loop is computable before the loop starts executing. Okay, and that's not the case here, because essentially we have no idea in general how many items there are in the list. So we cannot, or at least the runtime is not able to compute the number of iterations in the loop before it starts executing. So this is a case where tasks make it very convenient. Okay, so actually, if I just go back and look at this code, okay, it's not that you can't do this without tasks. It's just a little bit painful and not very efficient. So without using tasks in OpenMP, what you could do is, okay, you would have a loop that traversed the list and just counted the number of items in it, if that was something that you weren't already storing somewhere. Okay, so in general, you might not, you don't necessarily have to always have a variable that stores the length of the list. So you could traverse the list and just count how many items there are in it. And then you could traverse the list, you could then allocate an array of pointers of that size, and you could traverse the list again and store all the pointers to the items in the array. And then you could have just a regular for loop that traversed the array of pointers and called process on each of them. And then you could use a regular OpenMP parallel for that loop. Okay, so it's not impossible to do without tasks, but it means writing quite a lot of extra code, and also you get these two sequential traversals of the list to do the count of the items and to make copies of the pointers, and you've got extra memory allocation going on. So it's not particularly efficient way of doing it. However, with tasks, it actually becomes really quite nice and straightforward. So again, I'm going to use this parallel master pattern. So use the parallel region to create some threads to execute the tasks. Then just use the master thread only to traverse the list and package up the tasks. Okay, so just the master thread will traverse the list and use the task construct to identify the call to process as the independent piece of work that can be executed in parallel for each item in the list. Okay. So the one subtlety or the one tricky feature here that we have to take care of is this use of the first private clause here. So what this does is that it makes a copy of P when the task is packaged. Okay, so this is an instance of where we need not only the code inside the task, but we also need some data, associated with each task. And so what we need is for each task to have a private copy of the pointer, and for that private copy to have the value that it had when the task was generated. Okay. So in this case, so what first private does here is that it makes a copy of P for every single task, and when the task is generated by the master thread, it records the value, the current value of P in that private copy, so that when the task comes to get executed, it uses the right value of P, okay? Because otherwise, the master thread is going to carry on traversing the list and modifying P. So if P were a shared variable here, we'd have a race condition, and the task would potentially, or most likely actually, pick up the incorrect values of P that the master thread had carried on modifying. Okay, so just to kind of sketch and emphasize what's really going on here in this example, is, so thread 0 is essentially traversing the list and not executing anything, okay? It's just packaging up the tasks. All the other threads are inside the OpenMP runtime. They are essentially sitting in a while loop, waiting for tasks to appear, okay? So if you think what's, in terms of what the threads are doing, okay, the threads other than the master thread have no code to execute here, or so it appears. So they will skip over this master block and arrive at the barrier at the end of the parallel region. But before they enter that barrier, they have to check that there are no outstanding tasks. So, so instead of actually going into the barrier at the end of the parallel region, what those threads will do will actually go into a loop that says, okay, are there any outstanding tasks to execute? Okay. And then thread 0, once it's, if these tasks take a long time compared with traversing the list, then there's nothing to prevent the master thread also joining in. Okay, so master thread finishes generating the tasks. It can also then start executing some as well. Okay. So in general, again, we don't know, and the runtime is essentially in charge of swapping, and it's potentially this swap can happen before the end of at any point during this execution, is for thread 0 to swap from generating tasks to executing them and then back to generating them again. Okay, so in principle, we don't. This is all up to the runtime, so we have no control over what happens here. So all we know really is that by the time we get to the end of the parallel region, then we know that all those tasks have been generated and they've all been executed. Okay. So say this parallel master or parallel single is a very common pattern for using tasks, but that's not a restriction. It's perfectly possible for all more than one thread or all the threads inside the parallel region to generate tasks. Okay, so let's extend this example a little bit and say, okay, instead of one linked list, suppose we have an array of linked lists. Okay, so we have multiple linked lists, and we have an array that basically stores the first item in all the lists. So what we could do, okay, so now instead of just traversing one list, we want to traverse all the lists and call process on all the items. Okay. So what we could actually do is inside a parallel region, we could actually parallelize the generation as well. Okay, so we could share out the iterations of this loop over the lists between the threads. So different threads are going to traverse different lists and generate these tasks. So in this case, we've got instead of just having one thread packaging tasks and the other ones executing them, we now have all the threads in the parallel region both generating and executing in some order. Okay. So this is quite an interesting feature because otherwise this is quite difficult and potentially quite difficult in irregular parallelism to handle. So suppose our lists all have different lengths. Okay, so and also suppose that we're in a situation where the time it takes to execute process could be different for every item. Okay, so without using tasks, this would give us a very difficult load balancing problem to try and solve, and it's tricky to do with without tasks. Say you could, if you've got this kind of nested parallelism. Okay, so we've got two levels of parallelism here. We've got parallelism over the lists, and we've got parallelism over the items within each list. And if we have this kind of nested parallelism where both levels of parallelism have irregularity and load imbalance, then that's very difficult to handle with without tasks in OpenMP. So we'll talk a bit about nested parallel regions coming up in the next talk, but that doesn't really work for this if everything's terribly irregular. So this is an interesting pattern for this kind of problem, because we are essentially just specifying what are all the independent pieces of work, and we're leaving it up to the runtime to try and share out all those tasks between the threads in the parallel region and try and get some good load balance. Okay, so the tricky thing, or one of the tricky things about using tasks, is getting the data scoping right. Okay, because now we have the idea that variables can be shared or private or first private with respect to a task. So these concepts, well, they appear to be at first sight to be a little bit different compared with threads, but they're actually the same as what we have with threads if we think about nested parallel regions as well. Okay, so we'll talk about that in the next talk. But okay, so the rules are here, are like this. Okay, if a variable is shared on a task construct, the references to it inside the construct are to the storage with that name at the point where the task was encountered. Okay, so variable is shared. It means that we're just using the existing storage with that name, and not making any private copies for the task. Okay. So the complication here is that the what is the original storage could actually be something that is private to the thread that's generating the tasks. Okay, so we have so again we have this. We've introduced some nesting into this concept. So a variable, it's possible for a variable to be private to a thread, but shared between the tasks that that thread generates. Okay, so that's why it's phrased like this. Okay, so it's, the references are to the storage, whatever that happens to be it a shared or a private variable with respect to the threads. So whatever that storage is at the name, with that name at the point where the task was encountered. Okay, private is more straightforward. Okay, whereas private on a task construct, what we're getting is a new uninitialized copy of that variable with the lifetime of the task, just for the scope of the task. Okay, so it's same as for private for threads. You get a new copy when the task starts executing. It's uninitialized and it goes out of scope when the task has finished executing. For variables first private on a construct, then that's what we've already seen. So the references to it inside the construct are to new storage, but that's this new storage that's created at the point where the task is generated and initialized with the value corresponding to the existing storage with that name when the task was encountered. So that's the mechanism we've already seen to capture the value of the pointer to the current item in the list as we go along the list, and then use that for when the task is generated. Okay, so there are default rules here. So as with threads and parallel regions, there are default rules for data scoping, and they're different, okay, because the behavior you want for tasks is usually first private, but not always. So the defaults are different. Okay, so everything is first private except if they are shared in all constructs, starting from the outer parallel region. So this is a little bit complicated, and I'm essentially glossing over it because, as with parallel regions, I strongly recommend that you do not depend on the default behavior. Okay, so it's much safer to use default none. Okay, so the default none clause is available on the task construct, which forces you to declare everything that's referenced inside the task as either shared first private or private. And say, because reasoning about this is one of the difficult things about using tasks, so I cannot recommend using default none strongly enough. Okay. So another look at another example. So another pattern where task is useful is to exploit parallelism from multiple recursion. So this happens in a kind of pattern you get if you have tree-like or graph-like data structures, and you end up using recursive functions to traverse them. It's a very natural pattern for those kind of data structures. Okay, so this is every computer scientist's favorite but stupid way of computing Fibonacci numbers. Okay, so I fully acknowledge that this is an idiotic way of computing Fibonacci numbers, because it's order n squared, whereas there's a very obvious order n algorithm, but that order n algorithm is inherently sequential. Anyway, it just serves as a very nice compact example for recursion. Okay, so this code does is we have this recursive function fib. Okay, so we pass an integer into it, and okay, so if n is less than 2, then we simply return itself. Okay, so otherwise we call fib recursively with values n-1 and n-2, and then add the results of those two recursive calls together and return that. Okay, so then at the top level we need to kick off the recursion somehow. Okay, so if we're interested in computing the 5,000th Fibonacci number, then we could kick off the recursion. We could just pass 5,000 in at the top level and let the recursion do the rest. Okay, so again, a pattern which is tricky to implement without tasks in OpenMP. You would see again. So nothing is completely impossible, but you would need to rewrite this with a non-recursive implementation in order to use this as more standard features of OpenMP. Again, perfectly possible to do. You can essentially build your own task, build your own queue of and manage it and synchronize it correctly. It's doable, but it's tricky and requires a lot of changes to the code. Okay, again, with tasks, that makes it quite nice. Okay, so what we can do is we can identify each of the recursive calls as a task with the task directive. But then we need some synchronization here. So what we need to do is use, or what we can do is use the task wait directive here. Okay. So at this point, so remember, in general, we're already going to, because this is recursive, we're already inside a task. Okay. So, but this will wait for these two tasks. This will block until these two tasks have completed. Okay. And so what we're actually doing at each level of, so what we're doing here is basically generating a binary tree of tasks, of nested tasks. And so by using the task wait, the task cannot complete until all the tasks below it in the tree are complete. Okay. So, although task wait is just a shallow wait, we're just waiting for the children, but the children themselves contain the task wait for their children and so on. So we are in fact waiting for everything down below in the tree, but implicitly, because there's a task wait at every level, not because task wait, not because the semantics of task wait do actually wait for all the children, all the descendants. Okay. And then we can use the usual parallel master pattern to create the threads and to make the initial call at the top of the tree. Okay, the tricky thing here is the data scoping here. Okay, because by default, X and Y would be first private. We would be making copies here. But actually, that's not what we want. And to see that, it's a little bit is a little bit not obvious. Okay. So question is, okay, what are X and Y here? So X and Y are declared locally inside the function. So that means that every time we call this function, we get new copies of X and Y, which just have the scope of this function. Okay. But in order for these results to be visible when we come to add X and Y together, we don't want to make private copies for the tasks. Okay, so X and Y here inside the tasks must refer to the current existing storage called X and Y, which is the version or the copy of X and Y which was created by declaring them at this level in the recursion. Okay, so so that means that's why we have this shared clause here on these tasks for X and Y. So it means that this X and this Y really do refer to this storage here, not to some newly created storage for the duration of the task. And therefore, that when we come out, once the tasks have finished, then these values that have been returned really are in these variables, and we can add them together and return the sum. So that's slightly tricky and not obvious. Okay, so in general, think about using tasks. Yeah, so getting the data attribute scoping right can be quite tricky. Say, note that the default scoping rules are different from other constructs, but as I strongly recommend always using default none here. Okay. There's no real point in using tasks for things which are already or otherwise well supported by OpenMP. Okay, so for loops if you have loops that you can handle with work sharing, then there's really not going to be any advantage to using tasks because the overhead of using tasks is bigger. Okay, the the runtime has to do the packaging up of tasks, and it has to keep a track of them all internally somewhere, and then it has to schedule them to threads, and all that carries some overhead, which is in general bigger than what is required for scheduling loop iterations, even if you use a dynamic schedule for the loops. The overhead of tasks is going to be bigger. And also, I know, although the runtimes in general are quite good at scheduling tasks, you cannot expect miracles, okay? And in general, you may need to do something to your program to control the number and the granularity of the tasks that are generated. So, I mean, for example, in the in this Fibonacci example, the lowest level of task, okay, does practically nothing. Okay, it does an if test. So we're generating at the very bottom of the recursion, we're going to be generating tasks which have practically zero computation in them, which might not work out very well. So very often we find we have to do something to control the number of tasks, and basically, what are the naturally occurring tasks in the code or in the underlying algorithm may be too small, and you might need to group together the natural tasks into a bigger piece of computation, and define that as an OpenMP task. So the examples we looked at, for example, the list traversal, what you might find is that you actually, doing every single item as a separate task there might be not enough work in there. So you might need to rewrite your code so that instead of the process function acting on one item in the list, it acts on a number of consecutive items. Okay, so you could then, that would be, the task would now be a bigger piece of computation, and then the master thread needs to skip ahead so many items in the list before making the next call to process. And you can imagine that the call to process will internally have a sequential traversal of part of the list going on. So you might need to refactor your code in this kind of way in order to make sure that the tasks are big enough. Of course, you also need to make sure that you don't have too few tasks. If you have too few tasks, then the risk is that you don't have enough work to keep all the threads busy and well load balanced. Okay, and again, say for the Fibonacci example, then you might the lowest level tasks have almost nothing in them. So again, what the trick you could do here is to at some level in the recursion tree, you stop creating tasks and just let the recursion unwind sequentially below that point. Okay, so there's actually a little bit of convenient syntax here. The task construct takes an if clause, okay, and only if the if clause evaluates to true will it actually create a task. Otherwise, it'll just execute the code block sequentially. So we can put if n greater than some level, some value on the task. Okay, so if n is big enough, then we'll create tasks. Otherwise, we'll just do sequential recursion below that point. So that gives us control over, or it gives us a mechanism to control by choosing the value of level, how big the tasks are going to be, so it can stop creating tasks at some level in the tree and just combine all the recursive calls below that into a single task. Okay, that's the end of that one. Does anybody have any questions? Tasks are cool. Yeah, I agree. They are cool. They're slightly difficult to get your head around at first, but they are a very nice feature. Don't see them used a great deal in real codes, but there are a few where it's so if you have this kind of irregular or recursive parallelism, then so yeah, irregular nested or recursive parallelism can be handy. When would you recommend using task groups? Okay, so I guess there are some patterns where you want a deep wait, okay, where you need to wait. You've got nested tasks, and at some point you want to be able to wait for all the tasks that have been generated below that point. And then task group is the only real way to do that. Okay, unless you have this, this kind of trick with nested task. Nested task waits is a bit of a special case. Okay, and you wouldn't necessarily always want to do that. If you may not have that. That's useful in the Fibonacci type and the recursion case because you have that dependency. But there have been cases where that direct dependency on children at every level doesn't exist. And so you can have nested tasks without dependencies between different levels, and you just want to let all those children and grandchildren and great-grandchildren tasks execute without any synchronization, but you need to wait for them all to finish at some point. There is actually another use as well. So there's a restriction that says if you have a reduction variable on the parallel region, then you're not allowed to access that thing. You're not allowed to access reduction variables inside tasks. What you have instead is actually the ability to do reductions on task groups. So if you need to do a reduction operation across tasks, then you need to use a task group to do that. So there's some alternative. Basically, there's an alternative mechanism involving task groups to allow you to use reduction variables inside tasks. Okay, so if there's not any more questions, let's move on and talk about nested parallelism. Okay, so this is the idea of having teams of threads nested inside each other. Okay, so yeah, nested parallelism is supported by OpenMP. So what happens is if a parallel directive is encountered inside another parallel directive, or well, more accurately, within inside another parallel region, then a new team of threads will get created. Okay. In general, you need to do something to make this happen. So you can either use the OMP nested environment variable and set that to true, or you can call the OMP set nested routine inside the code to enable nested parallelism. But if nested parallelism is disabled, the code will still execute, but the inner teams will only consist of one thread. So your code still works, but when a parallel directive is encountered inside a parallel region, then that block of code will just be executed by the encountering thread, and it won't create any new ones. Okay, so we've got a Fortran example now. Okay, so example. So suppose okay, let's just focus on the loops here first. Okay, find my pointer. So we have two loops here, one of which sets some values in an array X, and the other sets some values in another array Y. Okay. So suppose what we would like to do here is not only execute these loops in parallel, but execute these two loops at the same time as well. Okay. So suppose we were running on, let's say we're running on a system with 8 cores, and so what we might like to do is to say, okay, can we devote 4 threads to parallelize this loop, and the other 4 threads to execute this loop in parallel at the same time? So the answer is yes. Okay, so that's by using nested parallelism. We could create an outer parallel region and arrange for that. I'll talk about how we control that in a minute. Arrange for the outer parallel region to contain 2 threads, and then depending on the thread number, either execute either go into this loop and create a new team of threads. Again, we need to arrange for that to be 4 threads going to execute this loop in parallel. Otherwise, if the thread ID is 1 at the top level, create another team of 4 threads to execute the J loop in parallel. So you could also use this particular example. You could also use sections. If you've come across that, you could also use the sections construct for the outer level here to specify these two blocks as independent blocks to be executed by different threads at the outer level. But I've just written it out explicitly with if tests here. So basically, that's the same example for in C. Okay, so in practice, you don't often need to use nested parallelism. Let's say it can be useful if we have algorithms or codes where there are multiple layers of parallelism available, but the outer one doesn't contain enough parallelism to keep all our threads busy or well load balanced. And there is some impact on performance by enabling it. Okay, so in order for the runtime to manage the possibility of creating and managing multiple teams of threads all executing at the same time, add some overhead in the runtime. So that's the reason that most implementations actually disabled it by default, and so you shouldn't turn it on unless you're actually going to use it, because it does create some not massive, does create some, in some cases, some noticeable additional overheads. So how do we control the number of threads at different levels? Well, one way of doing that is using the environment variable, because OMP num threads environment variable actually accepts not just a single value. You can have a comma separated list of values. Okay, So for that previous example, where I want 2 threads at the outer level and 4 threads at each of the inner levels, I can specify OMP num threads to be 2, 4, and that's what it does. Okay, so you can have any number here. So this is, so it counts from the outer. This is the outer level. This is the first nested level, and then you can have more values for subsequent lower nested levels as well. So that's okay, provided you want you want to set it outside externally to the program, and that you want the same number of threads at all the inner levels, which is probably the common case. But you can have more control if you want to. You can also call OMP set num threads inside the parallel region, or you can use the num threads clause on the parallel directive itself. So you can, in principle, do messy, complicated things like this. Okay, so I'll show the OMP set num threads version first. Okay, so again, so this is a little bit more complicated here. Okay, so supposing I'm having here is that I have a nested loop here. So the outer I loop only has 4 iterations. Okay, and the inner J loop has more. Okay, and so suppose I only want to dedicate 2 threads at the outer level, and then I want to choose, okay, for every instance, and potentially I can, for every instance of the inner regions, I can choose different numbers of threads. Okay, so if I have 2 threads at the outer level here, then what's going to happen is that each of those threads is going to execute for 2 values of I. Okay, so thread 0 at the outer level will execute I equals 1 and I equals 2, and thread 1 at the outer level will execute I equals 3 and I equals 4. Okay, subtract 1 for if you're a C programmer. Okay. So then in principle, I could, so this call to OMP set num threads happens in the master thread outside the parallel region. So that controls how many threads will be used at this outer level. And then once I'm inside that level, I can, every thread, and in fact here, every thread for every value of I could potentially use a different number of threads, which suppose I've pre-calculated and stored in some array. So in principle, you have this much flexibility, the ability to choose the number of threads, not only at each nesting level, but also for every single instance of every parallel region that ever happens inside the code. Okay, so if we call OMP set num threads, then the value set overrides the value in the environment variable. So what this is actually doing underneath is that OpenMP has this concept of internal control variables. And one of the internal control variables is called nthreadsVar. And that's what controls the number of threads that will be used for the next parallel region. And every single thread has its own copy of that variable. And that's what OMP set num threads is actually doing. It is setting the value of that internal control variable for the calling thread. So that's the number of threads that will be created the next time that thread encounters a parallel region. So this internal variable is a per thread value. And because OpenMP screwed up the concept of internal control variables wasn't in the very original version, wasn't in version 1 of OpenMP. So the naming of these functions got a bit screwed up because OMP set num threads sets this internal control variable, but OMP get num threads does not return its value. Okay, OMP get num threads returns the number of threads which are executing inside the parallel region. There's another function though called OMP get max threads, and that's actually what returns. That's actually the getter function for the internal control variable. So it's a bit unfortunate that that sort of naming convention got a bit screwed up. Okay, you can also achieve exactly the same thing using the num threads clause on the parallel region. Okay, so you can specify this doesn't change the internal control variable. It actually just overrides it for this current instance of the parallel region. So you can do it either way, and so the choice is really down to software engineering concerns. Okay, in some ways it might be quite nice to have the number of threads being used actually, lexically attached to the parallel region that it affects. On the other hand, if you've got code with hundreds of parallel regions in it, then maybe you don't want to use it on all of them. So in that case, the previous way, the OMP set num threads mechanism, be nice because you only need to call this once, and it doesn't have to be in the same program unit. It could be in some function that gets called in the initialization phase somewhere, for example. So it can be, you can squirrel this away somewhere else in the code. That's also a bit dangerous. So it's easy to it's easy to do bad things like leave. If you use this is to leave these calls around in the code with hard-coded values in, and it'll then always override whatever you set in the environment variable and so on. So there are choices here. Okay, so Matt's asking, this example, could we do a task over the first task with one thread over the first loop and task for everything else? Yeah, you could. I mean, in this particular example, as I come on to a minute, it really doesn't make sense to use parallel regions for this particular example. Okay, so tasks, nested tasks are actually in general more flexible and probably have lower overhead than creating parallel regions. It's a little bit hard to say whether which has bigger overhead, creating new teams of threads or using tasks. My suspicion is that tasks is probably both more flexible and more efficient if you can use them. Okay. I guess nested parallelism is one of the use cases for nested parallelism would be if you want to have if you really have some separation of levels into maybe a library. Okay, so if you're implementing a library and you want it to work in both scenarios. Okay, you want your library to do something sensible potentially if it's both called from sequential code or from inside a parallel region. So you might want to enable nested parallelism or use nested parallelism for library implementations. In which case, it would be kind of tricky to use tasks because then you are you can't it becomes harder to separate out what's in the user code versus what's in the library code. Other things, well, it's, with nested parallelism, it's easy to end up generating an awful lot of threads, and in general, we don't want to create more threads than we have hardware resources. So either would be that physical cores or virtual cores or hyperthreads or whatever. Generally speaking, we don't want to oversubscribe. So there's a way of limiting the OMP thread limit. Is just a way of limiting the total number of threads executing at any one time. Okay, so you can use that to basically prevent oversubscription of your hardware. You can also control the maximum depth of nesting that's used, and there are also a bunch of routines that let you navigate around the kind of tree of parallel regions that you've created. Okay, so there's OMP get level, which returns the level of parallelism in the tree. Okay, so it returns 0 in the sequential part of the program. So if you call it in the master thread outside any parallel regions, it returns 0, and then 1 inside the top level, and so on, and 2 inside the next level down. Okay. Get active level does the same thing, but it ignores any levels which are so-called inactive. So a level of parallelism is inactive if the team only contains one thread at that level. So this is kind of, this is how many levels deep I am in the tree of parallel regions, and this is how many levels deep I am in the tree of threads that actually got created at runtime, if you like. Then you can also get you can also inquire about thread numbers and team sizes at levels above you in the tree. However, there's yet another reason for not using nested parallelism is that this particular pattern or use case of nested loops is one where you might think, okay, perhaps I do want to use nested parallelism if I want to parallelize multiple loops in a nest. But actually, this other mechanism using the collapse clause is perhaps more convenient, provided the pattern matches this one. Okay, so the case that you can treat without nested parallelism is if you have so-called perfectly nested rectangular loops. Okay, so what does that mean? Okay, well, there's two parts to that. The perfectly nested bit means that there is no code in between. There are no statements in between the loops. Okay, so in other words, all the executable statements occur inside the innermost loop. So there's no code in between the fors, or no code between the ends of the loops. The rectangular bit means that the iteration space is a rectangle or hyperrectangle. In other words, it means that the bounds of the inner loops don't depend on the values of outside iterators. Okay, so in this case, if instead of j less than m, if I had j less than I here, that would not be a rectangular loop, because the bounds of j would depend on I. So what's going on here? Okay, so we can, if we want to parallelize both of these loops in this nest rather than just the outer one, then we can use the collapse clause here. So the argument here is the number of loops to treat in parallel, counting from the outside. Okay, so you could be in a situation where you have a nest of 4. You have a 4 deep nest of loops, but you only want to parallelize the outer 2. For example, the inner ones might not contain enough work, or they might have dependencies in them. They might be inherently sequential loops. So in this case, what will happen is the collapse clause will cause the compiler to create a single loop here of length n times n. So it'll replace this doubly nested loop with a single loop of n times n, and then fix up all the indexing inside. Okay. So that single long loop is what will get parallelized across threads, and it will also get, it's also the iterations of that single long loop is what is being used inside the schedule clause. Okay, it's what the schedule clause applies to. Okay, so if you specify a chunk size in the schedule clause, then that applies to iterations of the generated long loop. Okay, so when is this useful? Well, so in a situation where, say, the value of n is not big enough so that parallelizing just the outer loop might not have very good load balance. But then you say, okay, also, well, why can't I just parallelize the inner loop? Well, you could, but then you take a bunch of extra overheads for having lots more parallel regions and barriers. So you can. There are cases where this is useful. So if n is exactly equal to the number of threads, then you're okay. Okay, it's probably the outer loop would be balanced. But if n is a bit less than or just a bit more than the number of threads, which would mean that the outer loop wouldn't balance well, then you can use nested parallelism such that you can get better balance, because then you're essentially for a given I iteration, you're allowing is that some values of j will be executed by one thread, and other values of j to be executed by different threads. Okay, so that's effectively what you're allowing here, and it should produce better load balance. And for this particular pattern, then using the collapsed cause is likely to be much more efficient than using nested teams. Okay, and just to finish off this topic, you just need to think about how, if we use synchronization constructs inside nested parallelism, then there are some rules about how they apply, so barriers, either explicit barriers or implicit barriers at the end of work sharing regions, those only affect the threads in the innermost enclosing parallel region. Okay, so there's no way to have to use a barrier to synchronize across multiple teams. On the other hand, things like critical regions, atomics, and locks, they affect all the threads in the program. Okay, so a critical region will exclude threads, will force mutual exclusion between all the threads that are executing in any team. So critical regions are a bit, that might not be what you want. So if you want mutual exclusion within teams but not between them, then you might need to use, you might need to create a lock for every team, for example, or you could use atomics possibly. Okay, if the different teams are actually accessing different data items, then atomics would work, because atomics are just protecting access to the memory location rather than the actual execution of the code. Okay, any questions on nested parallelism? Okay, so how do private shared variables behave in the context of nested parallel regions? Okay, that's a good point. So essentially, it's the same idea as we saw with tasks. Okay, so you can have private or shared variables at all the levels of nesting. But it is possible, for example, to have a variable that's private on the outer level and shared on the inner level. Okay, so different threads will have their own copy of that thing at the outer level, but when we come to create the inner level of parallelism, then you don't get any new copies. The threads in the inner team will just use the copy from the thread that generated that parallel region. So in some sense, it's the same rule as for shared variables. It's the same rule as for tasks. Okay, what shared means is use the existing storage with that name. Okay, when the parallel region was encountered. And it's also possible to have, it's also possible to handle reduction variables in the same way. Okay, so you can have nested reductions. You can have a reduction, it's possible to have a reduction at the outer level and then specify the same variable as a reduction on the inner level, and you'll effectively get a nested reduction pattern. So you can do that as well. But yes, you do have this extra complication where things can be private at outer levels and shared on inner levels, or shared at outer levels and private on inner levels. So yeah, again, reasoning about that is a little bit more complicated, and it's yet another good reason for always using default none and forcing yourself to think about what the data scope attributes of everything should be. So Ian asks, does first private do any optimization when just reading variables? Does it read the shared variable and only allocate a new private version when doing a write? No, first private will always allocate and copy. First private has to happen even if you're just reading, okay? Because first private guarantees initialization of the private copies to whatever the value was. So it would be very difficult to do any sensible optimization there. But the standard does actually mandate that the copy must be made. Okay. In the very early versions of OpenMP, it was legal, for example, for the master thread inside a parallel region to use the shared variable as its private copy, but that's no longer the case. The specification enforces that private or first private always do make a new copy per thread or per task. Yeah, so the allocation of private variables is essentially free, okay? Because they are the mechanism that the runtime uses for that is just to put them on the stack. Okay, so every thread has its own stack, and the way that private variables are created is just by allocating them on the stack. And that's so cheap that you pretty much don't notice it. What you will notice costing is that if you make first private copies of large data structures, okay, first private copies of arrays, then the cost of making the cost is not in the allocation, the cost is in actually copying the values, because there really has to be a memory copy happening there. Whereas the allocation itself is essentially free. That mechanism also means that it's because things are stack allocated, you can also it's also relatively easy to end up with stack overflow if you are not careful about if you start allocating large arrays as private variables or as reduction variables, then you can easily end up blowing away your stack. I will talk later on. Yeah, this afternoon. Okay, I'll cover how to manage stack sizes in OpenMP. Okay, so last topic for this morning is the memory model. And essentially this is really just a warning, okay, of to just say that there are things that you might think should work in OpenMP or indeed in any other multi-threaded API and effectively don't. Okay. So what's this memory model thing anyway? Okay. Well, to appreciate that on modern computers, code is rarely executed in the same order as it's specified in the source code. Okay, because both compilers and processors and memory systems will reorder operations in order to try and optimize for performance. So when we're just executing sequential programs, all of that is completely unobservable, okay? Because the individual threads have to exhibit as if serial semantics, okay? So they have to produce the results that are specified in the source code, okay? So they have to behave, even though things get reordered, you can't ever observe you can't ever observe from the program results that that's happening. Okay, so our assumptions hold in face of depending, regardless of anything that's going on underneath. Okay, but when we come to multi-thread execution, things are not so simple. Okay, suppose we had this little pattern here. Okay, so we've got two threads, and let me find my pointer. Okay, thread 1 executes two statements. It executes x equals 1 and then y equals 1. And then at the same time, or at least without any synchronization between the threads, if thread 2 reads the value of y and then reads the value of x. Okay. So if no reordering happened, then we could have some guarantees, such as if thread 2 sees the value of y to be 1, okay, so if this read here returns the value 1, then we could guarantee that the subsequent read of x would also return the value 1 because x was written before y. So if no reordering was happening, that would be a valid assumption. However, if the code in thread 1 gets reordered, and from the point of view of correctness of thread 1's code, there's no reason why not to reorder those statements, because they're independent. Those writes are independent of each other. then we can no longer make that kind of assumption. So OpenMP supports what's called a relaxed consistency shared memory model. So what does that mean? Well, it means that threads are allowed to maintain a temporary view of shared memory. Okay, so a temporary view of the values of the contents of shared variables, which is not consistent with that of other threads. Okay, so it's possible that two threads reading the same variable could see different values at the same time, and these temporary views are only made consistent with each other at certain points in the program. They're not guaranteed to be consistent at all times. Okay. And as far as OpenMP is concerned, the operation which enforces consistency is called a flush operation. Okay. However, I should note that the OpenMP memory model has been significantly rewritten and extended as of version 5. What I'm really saying here applies to earlier versions of OpenMP, but it still acts to serve as a warning about what you can and can't expect to be able to be correct. Okay. So what does this flush operation do? Okay, so it defines a point at which a thread is guaranteed to see a consistent view of memory. So it guarantees that all previous read and writes by this thread have completed and are also now the results of those or any side effects of those reads or writes are now visible to other threads. And it also means at this point, no subsequent reads and writes by this thread have occurred. Okay, so this is what's usually referred to. So OpenMP terminology is a bit odd. This is usually what's usually referred to as a fence, a memory fence in other shared memory APIs. Okay. And you might think to yourself, well, how on earth did I ever manage to write a correct program? And given this flexibility for maintaining temporary views of shared memory. Okay, and the reason why everything works and you never have to care, or almost never have to care, is that this flush operation is implied by any time we do any sort of synchronization in OpenMP. Okay, so whenever we go into or out of parallel regions, whenever we have an implicit or explicit barrier, whenever we go into or out of critical regions, or whenever a lock gets set or unset, for example. So all these synchronization points in OpenMP also imply a flush operation. Okay. There are a few places where it doesn't, okay, so because there's no synchronization, okay, so entry to work sharing regions, the start of an OpenMP for or do loop does not synchronize threads and does not have a flush. Also, going in and out of a master region, again, there's no synchronization implied there, and also no flush. So thank goodness, you say, okay, that's sanity has been restored. Means that all the whenever we synchronize in threads in OpenMP, then we also guarantee that the views of memory between the threads are made consistent with each other. The problem only happens is if we try to use regular variables to synchronize threads. Okay, if we try to write our own code to do inter-thread synchronization without using OpenMP's inbuilt mechanisms. So a simple example of this would be this kind of producer-consumer pattern. Okay, so what we've got here is thread 0. Okay, it writes a value into a shared variable A, and then it sets a flag, supposedly to indicate that A has been written. Meantime, on thread 1, okay, thread 1 is spinning, waiting for flag to be true, okay, and then once it sees that thread 0 has set the flag, it then goes and reads the value of A. Okay, so in the hope or expectation that the value that this would guarantee that the value of A that's read here is indeed the value that thread 0 wrote. Okay. Unfortunately, we can't do this in the sense that this is incorrect code and may produce the wrong answer. Okay. What can go wrong here? Well, the compiler and all the hardware may reorder the read and write to A in a flag. Okay, because from the point of thread 0, there's no dependency between those writes. So it's perfectly legal for the compiler to reorder them. It's perfectly legal for them to happen out of order in the hardware as well. Other things that could go wrong, well, the compiler might decide to optimize this loop and only ever read flag once and then store it in a register. Okay, so in which case it'll never observe any subsequent change that happened on thread 0. It'll get stuck in there forever. Okay, so I think, right, okay, so if this isn't correct, can I fix it? Well, the answer is yes, but. Okay, so OpenMP actually has an explicit flush directive, so you can insert flush operations, and you can use this to make this example work, but I'm going to try and convince you that you shouldn't. Okay, so if we use flush, then what does that imply? Okay, and so in order for this kind of pattern to work, so for a write of a variable on one thread to be guaranteed visible and valid on a second thread, the following operations must occur in the following order in time. Okay, so there are 4 things that must happen. Thread A writes the variable, then thread A executes flush operation, then thread B executes a flush operation, and finally thread B reads the variable. Okay, so those are the rules we have to obey. The difficult one to enforce is the ordering between 2 and 3 here, okay? Because these are operations that are happening on different threads, okay? But we're trying not to synchronize those. We're trying not to use any inbuilt mechanisms to synchronize those threads. So how can we guarantee this ordering of flushes between different threads? So it turns out to be a little bit tricky. Okay, so we can do this example with flushes, but it's really unpleasant. Okay? And it's hard. It's a lot harder than you might think. Okay, so we need actually a lot more flushes than you might imagine. Okay, so let's look at them in turn. Okay? So on thread 0, this first flush is what that's doing is that this guarantees that the write to A and the write to flag are not reordered. Okay, so a flush guarantees that all previous writes have executed and no subsequent writes have happened. Okay, so that prevents any reordering of the assignment of A and the assignment of flag. The second flush is there to make sure that actually this write has really happened at this point, okay, and isn't arbitrarily delayed or isn't just stored in a register somewhere. Okay, so that has to, this is to make sure that that flag is actually gets written to memory at this point. On thread 1 side, okay, the first and these first two flushes are there to guarantee that every time that flag is accessed in this test, it's actually being read from memory. Okay, so this is for the first one, and this is for all subsequent ones. And then the really tricky one is this one. Okay, so this is what's actually ensuring the correct ordering of flushes. So this is make sure that the flushes that there's always a flush on thread 1 after the corresponding flush on thread 0. Okay, because otherwise, what could potentially happen is that thread 0 gets as far as setting flag equal to 1, okay, and the write has actually happened, but this flush hasn't actually executed yet, and then thread 1 basically has done this flush at some time in the past, okay, but then observes flag to be true, and then if it then went straight ahead and read A, then we wouldn't have got the correct ordering of flushes. Okay, we wouldn't have had a flush in thread 1 after this corresponding flush in thread 0, which is what's required by the memory model. Okay, it's kind of hard to visualize why this goes wrong, how this goes wrong, but it has to be there to obey the rules. And that's why programming with explicit flushes is really difficult. Okay, so it's hard, it's prone to subtle bugs. It's very difficult to test whether your code is correct or not, because it may execute perfectly correctly on one hardware platform or one compiler and not on another. And you can have something that's basically triggered by changing the optimization level on the compiler. Okay, so you can have code that works correctly, provided you don't turn on too much compiler optimization. You turn the compiler optimization up a notch, and your code breaks. Okay, so I'd strongly suggest that you really don't try and do this type of thing. Okay, that you are not tempted to try and roll your own synchronization constructs, and that you restrict yourself to using the ones that are provided by OpenMP. Okay. Having said that, for this particular example, there are ways around it. There's another way to do this, which uses atomic directives. Okay, so the version of atomic you're probably familiar with is for doing updates. Okay. So, doing things like, A equals A plus something. So the classic use of atomic directives in OpenMP is to protect updates to shared variables. But you can also do other things as well. Okay, there are other atomic operations. You can do atomic reads, you can do atomic writes, and you can also do atomic captures. So what a capture does is it applies to actually a pair of statements. So a capture will basically allow you to atomically read the old value of a variable and modify it in a single operation. So you're able to store the old value of X here into V and then modify it and have that whole pair of statements execute as an atomic thing. So strictly speaking, well, we should have used atomics anyway, because without it, then the accesses to flag in this is still actually incorrect OpenMP code. Why? because there's, technically speaking, there is a race on flag here. Okay, so that's flagged as a shared variable. It's possible for both threads, for thread 0 to write flag at the same time that thread 1 is reading it. So that's technically a race. In OpenMP, it's kind of hard to see why it would ever produce the wrong results, but we're not allowed to do it. Okay, OpenMP specification is very firm about what it allows in terms of race conditions, and that says you're not allowed any race conditions at all, no matter how benign or harmless they might look. Okay, so even if we do with flushes, then really we should have used atomics here anyway. However, there is a way around this. Okay, the atomics in the plain version of atomic does not imply a flush. It only guarantees consistency of the variable that's being updated, and not the rest of shared memory. However, it is possible there is this secconst, stands for short for sequential consistency modifier for the atomic directive, which does imply a full flush. So it actually is possible to code this thing correctly with using atomic reads and writes and the sequential consistency modifier. But again, that's quite tricky, difficult thing to get right, and strongly advise you not to try to do this unless you absolutely have to. So I should strongly recommend that you don't try rolling your own synchronization constructs. Okay, any questions about that? So again, it's really saying, I think my message is hopefully clear. Is you could consider designing your own synchronization mechanisms in OpenMP, but it's actually very difficult to get it right, and I would strongly counsel against doing it. Okay, so my apologies, I ran over very slightly in time there a bit, and so let's give ourselves a full half-hour break, and then the next session is basically for you to do some of the practical exercises. If you feel like it, no obligation to do it now, but if you want to do it now, and then myself and William will be available online if you've got any questions during the next session. But I'm going to have a break, and I strongly recommend that after all that you do as well. Okay, so we'll be back at 11:40 UK time.